Chemistry, Mrs. KJ here, going over 7.02, Unstable Isotopes. Have your notes ready. And just so you know, this lesson's going to be a little bit different as far as your note taking goes, because we're going to be talking about nuclear chemistry, which is really fascinating and goes pretty in depth. So what I'm doing is kind of a combination lesson, meaning I included a lot of the stuff from K-12, and I also included the stuff that I really need you to include in your notes. So there's going to be some extra stuff. So some of the slides are kind of on this background and some are going to look more like this, and I'll tell you along the way what you need to write down. So first thing, nuclear reactions. You should write all this down. Nuclear reactions change the amount of protons in the nucleus. This makes a new element. Almost all reactions you can think of are chemical, not nuclear. And if it's chemical, what is being exchanged or shared? So it's electrons are being exchanged, meaning that they are being gained, or they are being lost, or they are shared. Okay, so most of everything you can think of is chemical, not nuclear. So if we're talking about nuclear, now we're changing the nucleus. So very expensive equipment is needed for humans to do nuclear reactions. And I say humans because it happens in the sun. There's fission and fusion are examples, and radioactivity, radon gas, radioactive decay. So there are some ways that it happens naturally, but for humans to do it, it's very, very expensive equipment because you are actually going to split the nucleus. You're going to cut the nucleus of an atom. So, important scientist, you do not need to write this down, but I wanted to make sure I gave credit where credit is due, because as we set up here, a nuclear reaction, changing the amount of protons, we're breaking up the nucleus. Now, think about every time you've ever cut up vegetables or cut up a piece of food, okay? Throughout the history of mankind, billions and billions of times people have cut their food. Never once have they cut the nucleus of an atom. Okay, so kind of think about that for a second. Because I've thought about before when I've had gotten strawberries and have like 10 bushels of strawberries to go through, and I'm thinking, no matter how many times I pluck the end off the strawberry, I will never ever manage to split an atom. Never. Because if you did, what would happen? You'd have a nuclear reaction. You would have a mushroom cloud. This is what you would have if you split an atom, if you cut through the nucleus when you were cutting up your food, okay? You would not only explode, you would vaporize. It's a crazy amount of energy, okay? And it's never happened since the beginning of mankind when you're cutting your food that you cut an atom. And it never will happen because atoms are so crazy small. And the atoms of the knife that you're using to cut are spinning around, and the atoms of the strawberry are spinning around, and when you cut through they move out of the way no matter where you happen to cut it. So it's really mind-boggling to think about this. And it's my personality where I don't talk a lot about the actual scientists because I really want us to focus more on what they discovered and what they did and how chemistry works. But specifically, this scientist was put in the Minnesota State Standards. So I needed to mention her, and honestly, I didn't really know who she was because you don't hear a lot about her. Lise Meitner. And Lise Meitner, and I thought, why did they pick her of all the scientists? Well, when I read about her, she was working in Germany and Austria during the 1930s. Yeah, so she was in Berlin when all the stuff with Hitler was going on and World War II was starting, and she was Jewish. So she had to flee, and that's her picture. She had to flee Berlin, but she continued her work. And I'm also not big on quotes, but this is Madame Curie and her husband, Mr. Curie, Pierre Curie, who the two of them dedicated their lives to science. In fact, she died because of radiation poisoning because of all the work she did for science. And one of her quotes is, "We must not forget that when radium was discovered, no one knew that it would prove useful in hospitals. The work was one of pure science, and this is a proof that scientific work must not be considered from the point of view of the direct usefulness of it. In other words, it's not about the money. It must be done for itself, for the beauty of science, and then there is always the chance that a scientific discovery may become like the radium, a benefit for humanity. So it's amazing what they discovered and what they worked on, and really all these scientists. I mean, James Chadwick discovered the neutrons. Neutrons, things that don't have a charge, that we can't see. How crazy is that? And he figured out they were there. Henri Becquerel discovered radioactivity. The fact that this radioactive decay can happen, that there's stuff going to happen when an atom splits apart. And with Lise Meitner was Otto Hahn and Fritz Strassmann. And when uranium atoms bombarded by neutrons, they split apart. So they were the ones that figured this part out. The part of splitting a uranium atom when you threw neutrons at it. And when I say throw neutrons, there's a lot more to that. You can't just pick up a neutron and throw it at something and boom, have an explosion. Okay, so they dedicated their lives to science, and some amazing things happened, like the benefits of radium for medicine, which is also a Minnesota standard that we're going to talk about. So we know how this stuff has been so useful. So you don't need to have this in your notes. Sorry, I should have said that at the beginning. But just really want to give some credit where credit is due. They did some amazing things and dedicated their lives to science, and we've all benefited from it, even though we don't think about it very often, if at all. All right, so you don't have to write this part down, but this part is important. So in the nucleus, we have protons and neutrons, right? So they said the like charges of protons repel each other, causing the atomic nucleus to come apart. Think about when you put two magnets together. Okay, they either attract, but if you flip them around, they repel each other. Why? Because you have the two north ends together, or the two south poles together. Well, it's the same thing with the nucleus. They repel each other. They're two positives, so they want to be away from each other, but yet they're stuck in the nucleus together, and they're stuck being by each other. Why? How? Well, part of it is that the neutrons are there. The neutrons are in between the protons, and they're like, it's okay, guys. We know you don't want to be next to each other. All right, you can be next to us instead. And then look at these arrows. This arrows is showing that when you shove two protons together, they really want to be apart. But when they're next to each other, but the neutrons are in between, they're kind of like, all right, I don't really want to be by you, but, well, I just kind of want to get away from you because there's somebody else in between, so I don't have to sit right next to you and, look at you because there's somebody in between us, okay? Think about them having some attitude. They can't stand each other. They want to be away from each other. So if there's a buffer or someone in between, in this case, the neutrons in between, it kind of calms them down. And what it does is it reduces the repelling force in between them. So here's what I'd like you to add to your notes. If you'd like to draw the picture, go ahead. I think the picture is very helpful. So all protons are positive and repel each other, but yet they still stay in the nucleus. So every atom that has protons, which is everything except hydrogen, because hydrogen just has the one proton. So every other atom in the whole universe, the inside of it wants to be away from each other, but they stay together. Why? Reason number one, neutrons are between the protons. Since the protons have some space between them, the force pushing them apart is not as big. All right, so make sure you have that in your notes. The next reason has to do with this word, quarks. Quarks are what protons and neutrons are made of. You need to write this down too. Okay, and then we'll come back and we'll add some more to our reasons down there. So add down this vocabulary word, quarks, what protons and neutrons are made of. Okay, you do not have to write down this next part, but I wanted to show you a little bit about quarks. So protons and neutrons are made of particles that are still smaller, and they're called quarks. And what this is a picture of is, remember when I talked about up here about how Lise Meitner and Fritz and Otto worked together, and they said when the uranium atoms were bombarded by neutrons, they split. So I said they threw the neutrons at them. Well, you don't throw them with your hand. You use a particle collider. A particle collider, for example, like the Hadron Particle Accelerator, which is under Illinois, and I say under because it's like miles long and they build tunnels, and they make the parts of the atom go miles in circles and crazy fast, and they smash into each other. And after they smash, then this is a picture of what it looks like from the trails left over after they smash together. And it's actually really beautiful. And this is how they figured out that quarks exist. And if you want to hit pause and go ahead and read this, please go ahead. But that's how they discovered quarks. And so what they discovered is that if you look at a proton, there's 3 quarks inside of it. And the name of the quarks are up and down. I know, how original, right? So there's 6 kinds of quarks, and they have different names. And so the first 2 are called up quarks and down quarks. And instead of kinds of quarks, they're called flavors of quarks. Okay, I'm not making this up. This is really what it is. So there's the up quark, the down quark. There is the strange quark. There is the charm quark. And there is the top quark and the bottom quark. Ironically, the top quark was discovered last. So if you'd like to, you can pause and read some more about these. And so the quarks that we're going to talk about are the ones that make up the protons and neutrons. And it takes 2 up quarks and 1 down quark to make a proton. It takes 2 down quarks and an up quark to make a neutron. And the reason that they're showing you this is because the up quarks have a charge. Their charge is positive 2/3. Yeah, they're each positive 2/3. So if I add them together, I have positive 4/3. And then I have a down quark which has a charge of minus 1/3. So I have positive 2/3 plus positive 2/3 equals 4/3. Minus 1/3 gives me 3/3, or 3/3, which reduces to positive 1. So now it's kind of like, oh, no wonder why they're weird fractions, because when you add them together, you get the positive 1 charge. Neutrons are neutral, right? Well, that's because it has 1 up quark, so it's a positive 2/3, but look at this. It has 2 down quarks, so it's positive 2/3, minus 1/3, minus 1/3, put it all together, gets an overall 0 charge. Now, here's the second reason why the nucleus doesn't fly apart, why the protons don't fly apart. We had reason number 1, and I'll write down reason number 2, so for now you can just listen to it. It has to do with the quarks, okay? So the attraction between quarks holds the protons together. So this holds the actual proton together and is called the strong nuclear force. I know, how original. And it's so strong that it goes beyond the proton, and it pulls on quarks inside other protons. And this residual force, the fact that quarks are pulling each other together, and they're so strong they're pulling quarks of the next proton together, that's the residual or the leftover strong force. And that's the other reason why your protons are going to stick together inside the nucleus. And so if you're thinking to yourself, well then, if they're attracted to each other, how come everything in the whole universe doesn't stick together like one big glob? It's crazy strong, but it's only over a very short distance. Okay, so it's only strong enough to keep a proton together and then to attract to the quarks in the nearby neutron, in the other nearby protons, and just to hold an atom together. So it's crazy strong, but crazy short distance. All right, so if we go back to our notes, all protons are positive and repel each other, but they stay together in the nucleus. Why? Partially because the neutrons are in between and like, hey guys, it's all right, I'll sit between ya, so then they don't repel each other as much. And then the second reason is the strong force. The extremely strong force of quarks attracting, so that's what holds the protons and neutrons together, and the leftover strong force called the residual strong force that causes quarks of one proton or neutron to be attracted to quarks of another proton or neutron in the same nucleus. So not only are the quarks keeping this proton together, but the force is so strong there's a little bit of a pull left over, and it keeps it near this neutron. And this neutron's kept together by the strong force of its quarks, and it's so strong, it's like, oh, yep, come here, proton, come here, proton. And so it's a force within